Today we are gonna start final presentation about St. Mary's design and construction. The site of the St. Mary's building is where the Baltic Exchange was originally located. However, it was collapsed by terrorism in 1992 and a new landmark building was planned on the site to promote London's revival. The city wanted to build a building there with an innovative design that could represent London, which could be a new landmark. And Norman Foster, a master of high-tech architecture, was chosen as an architect to design the city's new landmark. So, what kind of architect is Norman Foster? Norman Foster is an architect who is interested in two things: high-tech architecture and eco-friendly. HSBC Hong Kong's main building challenged high-tech architecture, and London City Hall was interested in eco-friendly issues and designed sustainably. Norman Foster, who built such a building, also pursued this philosophy in St. Mary's. St. Mary's building used diagrids to implement innovative structure designs and designed buildings that reduced energy consumption considering sustainability. St. Mary's is located in the City of London in the United Kingdom. The building has a unique oval appearance by utilizing its diamond structure. The design is characterized by a thick center part and a thin bottom part. So the design was able to put as much public space as possible on the building's ground level. In addition, the curved design is designed to minimize the impact of wind loads and to avoid turbulence in the city center. This allows the building to harmonize with the city environment while maintaining structural stability. These innovative designs have made the St. Mary's building an iconic landmark that defines London's skyline. St. Mary's is a high-rise building with 40 stories, 180 meters. The top three floors of St. Mary's are located in a restaurant and a bar with panoramic views of London, while the 3rd to 34th floors are planned as offices. St. Mary's has an open office space through a characteristic structure using a diagrid. Let's look at that through a plan view. St. Mary's has a circular cross-sectional design. Natural light enters in all directions, securing the right to view, increasing openness. It was able to simplify the movement through the center core. Space utilization was increased through the efficient arrangement of elevators and staircases, which are facilities. And 6 void spaces on each floor was used as atrium to promote openness and air circulation. As such, St. Mary's has created a pleasant and efficient office environment through innovative cross-sectional design and space utilization. Construction of a building begins with the foundation. What are some important considerations before constructing the foundation? Have you ever heard about the etymology of London? As an answer, there is a story that it was created by combining Lynn, which is next to a lake or stream, and Dun, which means city. There are many stories about London's etymology, but the common meaning is that it's an area with humid land. Go back to the building. St. Mary's was built on soft ground made up of acidic soil and wet soil. Therefore, you have to pay attention to the differential sediment that can occur on soft ground. Therefore, the St. Mary's building requires a lot of files in a large size. The specification of the file is 27 meters high and 750 millimeters in a diameter. The total number of files is 333. The file used in the cast-in file method. Through the construction of the files, constructors began laying the foundation for the St. Mary's building. The constructor installed the files on the land. After that, the file caps and files were connected so that the load of the building could be effectively distributed. First, dig out the soil of the site and supported with a mud barrier wall and a brace to prevent it from collapsing due to earth pressure. Then put the file around the edge and center. Rebar is placed on the embedded file and concrete is placed on it a short period of time. When the foundation is completed, the body of the St. Mary's building will be built. Gravity load, wind load, and seismic load are important considerations for skyscrapers. The main structures of the St. Mary's building consist of a core and a diagrid, which has many advantages in load distribution, which is an important consideration. St. Mary's building is a skyscraper which can be relatively less rigid as its height increases compared to lower-rise buildings. In order to increase the robustness of the core, it was designed by dividing it into an inner core and an outer core. In addition, the interior space was left empty to accommodate facilities such as stairs and elevators. The inner core is composed of A-shaped steel connected to the columnar part of the foundation and serves as a pillar. St. Mary's diagrid serves to effectively distribute its own weight, seismic load, and wind load. This is one of the important parts from a structural point of view. This was directly connected to the main part of the building site, so that the load could be distributed to the ground. Diagrid construction is largely composed of nodes and diagonal members. The A-frame of one node and two diagonal members is one unit that constitutes a diagrid structure. In addition, the building's A-frame consists of two-story triangular module. When a load is applied to the unit, the load can be effectively distributed from the node to the diagonal member. Nodes are connected to other nodes through a ring beam and are connected to the core through a radial beam. Through this connection, the load can be effectively dispersed to the core by descending along the diagonal member of the diagrid. This A-frame could be stably constructed through connection with the core using a beam. The connection process has three main procedures. First, install the A-frame. Second, connecting the core to radial beam. Third, horizontal beam connection. First, frame A is vertically erected. Then it is connected to the core through a radial beam, and nodes are connected using a ring beam. Therefore, by repeating this process, frame A is continuously coupled to form a steel structure that moves intervally. When the construction is completed as the diagrid structure rises to the top of the building, the construction of the top dome begins. Unlike the main body of the building, the dome section, which is 22 meters high, is designed with a truss structure without nodes. The dome is mainly used as large, open space, such as restaurants and observation decks. The diagrid nodes have limited space utilization because they are connected to the core, but the use of the dome, which is truss structure, will give enough space. The construction of the dome part is as follows. Assembly the truss module on the ground floor. It is then moved to the roof using a crane and connected to the diagrid. A total of 18 truss modules are joined together by welding. Finally, the construction of the steel structure is finished by putting only the circular cap to decorate the finish of St. Mary's. How did the diagrid distribute loads efficiently? The higher the building, the more affected by the wind load, so the area of the upper layer was gradually reduced to control the wind flow and maintain structural rigidity. For this reason, in order to achieve the optimal load distribution considering the area and height of each floor, a node angle of 60 degrees was adopted in some floors and 77 degrees in others. These nodes were arranged in 18 units across each of the 2 floors, and a total of 360 nodes were used. In addition, the stability of the structure was increased by using the highly rigid HSS diagonal member, and the sizes of the upper and lower layers were set differently, enabling more efficient and accurate load distribution. What kind of efforts have been made to reduce construction errors? First of all, in order to reduce the error in the fastening of the node and the diagonal member, the factory accurately processed the junction of the node and the diagonal member through the CNC milling method and the slot hole method. The factory-made diagrid is placed at the correct location of the members to maintain the adhesion and spacing of the node and the diagonal member at the site, and then constructed through temporary tightening. After the overall connection between the diagrid and the core, the slab construction is carried out. This process is constructed using deck plates, stud bolts, wire mesh, and concrete. First, connect the deck plate to the radial A-shaped steel beam. Weld the stud bolts, lay the wire mesh, and finally pour the concrete. At this time, the stud bolt guarantees the integral behavior with the concrete. Particular attention was paid to the usability of steel structure in the case of the St. Marys building. To reduce the weight, Litex lightweight concrete was used to reduce the weight of the structure by about 23%, which contributed to the result below the maximum sagging value calculated by the general sagging formula. In addition, for lighting efficiency and atrium space optimization, the floor plan was rotated by 5 degrees to create void spaces at intervals. Next, let's look at how the curtain wall of the building was constructed. The exterior of the building, which has a round shape, is all designed with oblique steel beams and 5,500 double glasses in the form of diamonds. The spiral striped diamond pattern on the exterior further emphasized the building's natural lighting and ventilation functions. In addition, the curtain walls of buildings maximize natural ventilation and energy efficiency. Due to the nature of London's weather, which has many cloudy and rainy days, the curtain walls of buildings had to take full advantage of the lighting effect. Therefore, by controlling the indoor temperatures through solar management through the curtain walls, it resulted in energy savings about 40%. The curtain wall of the building used the unit wall system. The exterior of the building is covered with a diamond-shaped facade. On the horizontal beams located in layers, brackets for substructure members of curtain wall finishes were planned. Each facade was pre-made in a factory and shipped to the construction site. Then, in the field, constructors connected the facade to the bracket part installed on the diamond-grade frame using bolts. The waves on the upper part of high-rise buildings were moved by a crane and connected to the frame in the same way as above. Double glazing glass were used for the skin module of the curtain wall. Double glazing glass was able to increase the sustainability of St. Marys. Double glazing glass allowed us to increase the energy efficiency of St. Marys. It consists of inner panel and outer panel glass, which reduces the direct solar heat effect, and fills argon between the glass to significantly reduce the convection phenomenon of air, thereby reducing the heat exchange phenomenon inside and outside the window. In addition, the low E coating reduces the ability to block heat entering the interior and condensation by 4 to 20 times lower than that of ordinary glass. The building induced sunlight to enter the entire building through transparent diamond-shaped panels. The sunlight coming through the curtain wall could be effectively spread by the inner light well. The light well is not in the form of general glass ceiling, but a void space is drilled into a slab on each floor so that the lower and upper floors could be connected. This allows natural light to permeate all spaces through the light well, depending on the planar configuration that rotates 5 degrees spirally. This had the effect of naturally improving the difference in illuminance between the center and outside of the building, allowing sunlight to enter the inner office. After the complete construction of the building was completed, there was a question of how St. Maria's applied a different energy efficiency system than other buildings. Designed by Norman Foster, St. Maria's is a representative green building that introduces a number of innovative systems to increase energy efficiency. What is a green building? A green building is a building that reduces energy load and improves energy efficiency. So what approach did St. Maria's adopt to improve energy efficiency? As the table shows, lighting, cooling, and ventilation account for more than 60% of electricity used in most offices, and heating mainly uses natural gas. To reduce this energy consumption, Norman Foster designed to use natural ventilation to reduce the energy consumption used for heating and cooling in buildings. St. Maria's heating, ventilation, and air conditioning systems take full advantage of natural ventilation to reduce cooling and heating energy use. Each floor of the building has a unique shape that turns 5 degrees, so it can accommodate more natural light. This reduces the amount of energy used for indoor lighting. And the St. Maria's has a double skin. There is a space between the outer and inner curtain walls, so air circulates into this space. This prevents hot air from directly entering the building in summer and reduces the heating load by acting as an insulation layer in winter. And the automatic blinds are opened and closed according to the amount of insulation, adjusting the internal temperature. How does air circulation work? The answer is the stack effect. The warm air inside the building has a tendency to rise, which is why it is used. The window automatically opens when the outside temperature is 20 to 26 degrees and the wind speed is less than 10 mph. Through this open window, the heated air inside the building rises and escapes. This creates negative pressure in the lower part, and fresh outside air flows into the open window in the lower part, resulting in circulation. In this way, the St. Maria's using natural ventilation was able to keep the air inside fresh with less energy consumption. These sustainable eco-friendly systems have enabled St. Maria's to halve the energy it uses compared to similar-sized buildings. Today, we looked at St. Maria's innovative architecture technology and eco-friendly design using Diagrid. St. Maria's elegant curved design and unique shape have become a new landmark on the London skyline. Despite of enormous size of 40 stories, its flexible silhouette has become a signature of St. Maria's. After all these efforts, St. Maria's has now become a new landmark in London and an example of eco-friendly architecture. It is contributing to environmental protection by reducing carbon dioxide emissions by 25%. We think these pioneering structures will increase the sustainability of city as a whole and point to the future of construction. Thank you for listening to the presentation.